Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be looking at boundary value problems. So we've been doing initial value problems, and for those, all of the conditions are specified at the same value of the independent variable, and we can use the Runge-Kutta method as probably the most useful technique for solving those. Well, for boundary value problems, the conditions are going to be specified at different values of the independent variable, and so Runge-Kutta won't work. Now, there are some methods that will work, and the ones we're going to discuss are going to be the shooting method, finite differences, and eigenvalues. So first, I have an example boundary value problem. This is out of a textbook on numerical computing by Chapra. But basically, it's looking at an energy balance on a long, thin rod. It's not insulated along the side, so you're going to have heat loss along the length. That's described by the heat transfer coefficient H prime. And the surrounding air will be TA, T ambient. And we want to know the temperature as we move along the rod if we have a fixed temperature at each end. And so in this particular case, we've got surrounding air at 20 degrees C. We have a 10-meter long rod. On one side, it's 40 degrees C, and the other is at 200 degrees C. And we'll use an H value of 0.01 meters squared. Now, the energy balance for the conduction with the convection heat transfer is going to give you d2t dx squared, so the second derivative of t with respect to position, plus h prime times Ta minus T, the temperature differential for the convection, is equal to 0. And the boundary conditions are that the temperature at position 0 is T1 and the temperature at position L is T2. Now this is one that can be solved analytically, and this is the example or this analytical solution to this example problem. So with these values, you end up with this. And you can graph this answer and do this to compare to what we get numerically from these next techniques. So first, let's look at the shooting method. Now, what the shooting method is it converts your boundary value problem into an equivalent, and that should say initial value problem right here. So you're going to take the second order ODE and turn it into a system of two first order ODEs like we did in the last lesson. So z is dt dx and the second derivative is dz dx, and so that's equal to h prime times t minus ta, switching that order of subtraction there. And we know that t of 0 is equal to 40, but I don't have an initial value for z, so I'm going to guess. Okay? What you're going to do is you're going to guess, you're going to solve the equation using Runge-Kutta and find out what t at 10 is and see if it matches, and it won't. And so then try a second guess and again figure out what is t at 10. So when you use z of 0 is 10, you ended up with t at 10 is 168. And when you guess that z of 0 is 20, you get t of 10 is 286. Now we know the actual answer is 200, and so if the equation is linear, this one is, you can use interpolation to get the correct answer. But in general, the equation will not be linear, and so this gets you an estimated value of z naught. And you can run the program one more time, and then that will get you your full solution. Now this is only an estimate, so if your equation is nonlinear, this won't be exactly right, but it will get you closer, and you can do sort of a half interval method like what we were doing back when we were solving systems of, or not systems, but solving equations, finding roots of equations earlier in the course. So this is the shooting method. The idea is that you've, thrown a clay pigeon up there and you're shooting at it, trying to guess where it's going to be. So did you hit your target or not? The second method that's useful is the finite difference method. Now, for finite differences, what we're going to do is replace the derivative with a really simple delta approximation. So it would be ti minus 1 over delta x would be dt dx. For a second derivative, we get ti plus 1 minus 2ti plus ti minus 1 over delta x squared is the second derivative. And then all the other terms evaluate at ti. And we'll use this essentially to approximate what ti is. Unfortunately, it's in terms of two of these other terms. And so therefore, what we need to do is algebraically rearrange this so that we get the t's collected together. And so that's what you see in this equation. Now, if you do this and you do it for every point along the rod for however you've decided to divide up delta x, you end up getting a matrix. Now, for the sake of simplicity, we're going to use a really big delta x. Delta x is 2 meters. And so if you do that, then the coefficients of the T1s are in this first column, T2 in the second, T3 and T4. We know already, and those are incorporated into this 2.04, we knew what T0 was, and we know what T5 is. And so therefore, I only end up with these terms here. The other values are wrapped up in these coefficients. And so when I do this, this is now just going to be a matrix problem. It's a linear system. And so all I need to do is do the inverse of A times the B matrix, the 40.8, 0.8, etc., that one. And I'll get my T column vector. And so these are the answers that you get, and they actually fall very nicely in line with the solution. You can do a better job, you'll get a better approximation as you choose smaller and smaller delta x. The last technique is using eigenvalues. Now that's really too big a topic for the last week. So I'm going to just rely on the fact that you actually do have a solid math background somewhere back there and you could look this stuff up. But the key thing is that you are introducing an eigenvalue, which is going to allow you to come up with your eigenvectors, which determines the form of the solution. The part that is mathematically challenging is solving for the lambda I. But it's just a matrix equation. And so we can use our Excel to find values of lambda that satisfy this. And then use the math, and that tells you what the forms of the solution are. Now I am going to post a handout that has an example problem worked out on this one, just for the sake of completeness. But I just wanted to make you aware of this technique, and that really the only thing that mathematically is challenging is solving this equation. And we can get our numerical computation programs that we've already written to solve that for us. So this concludes our lessons on boundary value problems. Thank you very much for your time.